Hello students, welcome to EPG Pathshala. I am Dr. Aditya Saxena from the Department of Physics, Central University of Haryana. Today, we are going to discuss about a module, Orbital Angular Momentum and Spherical Harmonics 2 under the paper Quantum Mechanics 1. So students, let us see what all we're going to be learning in this module. We'll start with the spherical harmonics under parity operations. That is, we'll try and understand how the parity operations affect the spherical harmonics. Then we'll move on to the explicit representations of spherical harmonics for a few lowest values of the orbital angular momentum number L, and we'll then try and draw the polar plots of the probability density distribution. From there, we'll then move on to the vector model for angular momentum vector L. Having understood the vector model for angular momentum vector L, we'll then try to find out the wave functions of a particle on a sphere. That is, when the particle is constrained to move on a sphere. And as an example to this problem, we'll study the rigid rotator. So, in this module, this is a direct continuation of the preceding module on orbital angular momentum. Having studied some important properties of spherical harmonics, we shall turn over to study the behavior of spherical harmonics under parity operations. We shall also study explicit representations of spherical harmonics for a few lowest values of the orbital angular momentum number L, giving the polar plot of the probability density distribution. In the next section, a vector model of angular momentum is going to be discussed. Finally, as a simple illustration to the application of spherical harmonics, we discuss motion of a particle on the surface of sphere and apply it to the case of a rigid rotator. Parity operation on the spherical harmonic YLM. Now let us study how the spherical harmonics behave under parity operations. First of all, let us understand what are parity operations. So parity operation basically means that when any function goes from a value, that is, if there is a function which is a function of radial operator or a radial vector, and that radial operator or radial vector goes from r to minus r, then how does the function's value change? So this kind of a operation where the function or the independent variable changes its value from plus to minus, and we try to see that how it affects the dependent variable, such an operation is called a parity operation. So the wave function under parity operation changes as psi prime r comma t, that is, wave function psi prime as a function of vector r and time t is equal to parity operator times wave function psi as a function of vector r comma t is equal to psi as a function of minus vector r comma t. That is, that when the parity operator acts on the wave function, it changes under the operation vector r going to minus vector r. In terms of this polar coordinates, the parity operation changes the angle theta as angle theta goes to pi minus theta, and the parity operation changes the angle phi as angle phi goes to pi plus phi. Thus, Parity operator acting on the spherical harmonic YLM theta phi will return the spherical harmonic YLM pi minus theta, comma, pi plus phi. Now, we know that the spherical harmonic YLM theta phi is represented in terms of the Legendre's polynomial as minus 1 to the power m times PLM cos theta exponential to the power iota times m phi. Now, as theta goes to pi minus theta under parity operation, cos theta will go to cos pi minus theta, which is equal to minus of cos theta, and sin theta will go to sin theta only. That means sin theta under parity operation will remain unchanged. So the factor 1 minus x square whole to the power modulus of m by 2 is equal to sin theta, sin modulus to the power modulus m theta, and this term in the Legendre's polynomial PLMX remains unaffected under the parity operation. However, the polynomial factor acquires a sign which is given by minus 1 to the power L is equal to modulus m. However, the polynomial factor acquires a sign which is given by minus 1 to the power L minus modulus m, with the result that the spherical harmonics YLM theta phi goes to minus 1 to the power L minus modulus m plus m times YLM theta phi, and this turns out to be equal to minus 1 to the power L YLM theta phi, since m is an integer. Thus, the spherical harmonic YLM theta phi has a parity minus 1 to the power L. Representations of spherical harmonics. Now, the spherical harmonic YLM theta phi has a parity minus 1 to the power L. So, this spherical harmonic is odd, or the parity is odd, or will take odd values for odd values of L, and will take even values for even value of L, which means if L is odd, then minus 1 to the power L will give a negative or an odd value, and if L is even, then minus 1 to the power L will give a positive or an even value, and this parity will correspondingly be taken by the spherical harmonic Lm. It is important to note that the operator P with operator L square and Lz, in fact with all components, can be seen as operator P acting on operator Lz acting on the wave function psi as a function of vector r comma t is equal to minus iota times h cross times operator P acting on within brackets x times del by del y minus y times del by del x bracket close whole times psi as a function of vector r comma t, where vector r is the position or the radial vector and t is the time component. This relation turns out to be equal to operator P acting on operator Lz acting on the wave function psi as a function of vector r comma t is equal to minus iota times h cross bracket open minus x times del by del of minus y minus within brackets minus y times del by del of minus x bracket close whole acting on psi as a function of minus vector r comma t, and this turns out to be equal to operator Lz acting on wave function psi as a function of minus vector r comma t is equal to operator Lz acting on operator P acting on wave function psi as a function of vector r comma t, where operator P is the parity operator and operator Lz is the z component of the orbital angular momentum operator. And from this, one can also get explicit representations of a few spherical harmonics of the lowest L values. And looking at these, one can note that these are complex. So, for example, if we look at the spherical harmonic y2 plus minus 2 theta phi is equal to under root 15 by 32 pi times sine square theta times exponential to the power plus minus twice iota times phi. However, if one takes the absolute value of the spherical harmonic modulus of y lm theta phi, then it turns out that this absolute value is real and is independent of the angle phi. Plots of probability distribution. The polar plots of the probability distribution or the probability density distribution function, that is modulus, that is square of modulus of y lm theta phi, or the square of the modulus of the spherical harmonics, can be seen for different values of m and L, where m is the magnetic orbital angular momentum number and L is the orbital angular momentum number. So the first of these plots is for m equal to 0 and L equal to 0, and we can see that in this plot it's a circle. The second plot denotes the case of two cases corresponding to L equal to 1. So for L equal to 1, m can be equal to 0 or 1. So for here we have considered m equal to plus 1, otherwise m could be equal to plus minus 1. So here the cases that is considered is m equal to plus 1. So for L equal to 1 and m equal to 0 case, we see that it's a dumbbell kind of a shape with the node occurring along the x-axis or the horizontal axis. Whereas in case of m equal to plus 1 and L equal to 1, again it's a dumbbell kind of a shape with the node occurring on the vertical or the z-axis. Then if we look at the next case, that is L equal to 2, here we have three graphs corresponding to m equal to 0, m equal to plus 1 and m equal to plus 2. So for m equal to 0, we have the first graph, for m equal to plus 1 we have the second graph, and for m equal to plus 2 we have the third graph. And finally in this graph or in this plot we can see the case for L equal to 3, and here four different plots are given. The first plot corresponds to m equal to 0, the second plot corresponds to m equal to plus 1, the third plot corresponds to m equal to plus 2, and the fourth plot corresponds to m equal to plus 3. Vector model of angular momentum. Now let us consider a particle in the angular momentum state ket vector Lm, and the angular part of its wave function psi, which is normalized to unity, is given by the spherical harmonics y Lm theta phi. We have already seen that the eigenvalues corresponding to the eigenvector Lm, when the operator L square acts on the eigenvector or the ket vector Lm, it returns the eigenvalues h cross square L into L plus 1 times the ket vector Lm. Similarly, we have also seen the eigenvalues for the operator Lz, that is the z component of the orbital angular momentum operator. The z component of the orbital angular momentum operator Lz acting on the ket vector Lm gives h cross m times ket vector Lm, where h cross m is the eigenvalue corresponding to the operator Lz acting on the ket vector Lm. So using these two relations, one can then write down the expectation value of the ladder operator for the orbital angular momentum operator, that is operator L plus and L minus, as expectation value of the operator L plus, which is bra vector Lm operator L plus acting on ket vector Lm, is equal to h cross times bracket open, L into L plus 1 minus M into M plus 1 bracket close to the power half times bra vector Lm ket vector Lm plus 1. Similarly, the expectation value of the ladder operator L minus is given by bra vector Lm ladder operator L minus acting on ket vector Lm is equal to H cross times bracket open L into L plus 1 minus M into M minus 1 bracket close whole times to the power half times bra vector Lm ket vector Lm minus 1. So now looking at the eigenvalue equations of L square operator and Lz operator and the expectation value of the ladder operators L plus and L minus, one can see that the expectation value of the z component of the orbital angular momentum operator, that is bra vector Lm operator Lx ket vector Lm, is equal to half times bra vector Lm operator L plus plus operator L minus acting on ket vector Lm, and this gives the final result as 0. Similarly, if we find out the expectation value of operator Ly, that is the y component of the orbital angular momentum operator, so we find bra vector Lm operator Ly ket vector Lm, and this also turns out to be equal to 0. However, if we look at the expectation values of the operator Lx square and the expectation value of the operator Ly square, we find that the expectation value of the operator Lx square, that is bra vector Lm operator Lx square ket vector Lm, is equal to the expectation value of operator Ly square, that is bra vector Lm operator Ly square ket vector Lm, and this turns out to be equal to half times bra vector Lm within brackets operator L square minus operator Lz square acting on ket vector Lm, and this turns out to be equal to half times bracket open L into L plus 1 minus M square bracket close times H cross square. Note that when M is equal to plus 1 or M is equal to minus 1, vector model of angular momentum. Note that when M is equal to plus L or M is equal to minus L, that means the value of the magnetic quantum number is equal to either plus L, the orbital angular momentum number, or minus L. Then, that is, Z component is parallel or anti-parallel to the Z axis. Then, its X and Y components are still not 0, though the average is 0. It is convenient to visualize the results in terms of the vector model, according to which the orbital angular momentum vector L of length under root L into L plus 1 times H cross precesses about the Z axis. The two L plus 1 allowed values of its projection of the orbital angular momentum vector L on this axis being given by the M times H cross values, with M being equal to minus L plus 1 and so on till 0, then 1, 2 and so on till L minus 1 and then L. That means M takes 2L plus 1 different values for each value of L. Then, as we have seen, the vector L, that is the orbital angular momentum vector L, may be viewed as lying on the surface of the cone with the altitude mh cross, where m is the magnetic quantum number and h is the Planck's constant, which has z-axis as its symmetry. All orientations of the orbital angular momentum vector L being equally probable along this axis of symmetry. Particle on the surface of a sphere. Now let us consider the case of a particle on the surface of a sphere, which we normally know as the rigid rotator. That is, the particle is constrained to move on the surface of the sphere. Such a particle is, or rather such a configuration is known as the rigid rotator. So in order to study the rigid rotator, let us consider a simple example of a particle of mass mu, and let the linear momentum vector be defined as minus iota times h cross times del vector. That is, the momentum operator is defined by the above equation in the position representation or the Cartesian coordinate representation. Then for such a momentum operator, that is for such a linear momentum operator, the kinetic energy operator of this particle is given by, kinetic energy operator is equal to operator p square by 2 mu, and this is equal to minus h cross square by 2 mu del square. Now expressing the del operator in spherical coordinate system, we can write the kinetic energy operator of the particle having mass mu as operator t is equal to minus h cross square by 2 mu bracket open 1 upon r square times del by del r acting on r square times del by del r plus 1 upon r square sine theta times del by del theta acting on sine theta times del by del theta plus 1 upon r square sine square theta times del 2 by del phi 2, or the double derivative of the partial differentiation with respect to phi whole bracket close. And this can then be written as the kinetic energy operator is equal to h cross square by 2 mu bracket open 1 upon r square del by del r acting on r square times del by del r minus operator L square upon h cross square r square bracket close, where we see that the operator L square is given by the second and the third term of the above equation. So if a particle is constrained to move on the surface of a sphere, then the radius of such a movement will always be fixed, having a value equal to the radius of the sphere, that is r is equal to a, and therefore the first term does not contribute. As a result, the kinetic energy reduces to operator T is equal to operator L square by 2 mu times a square is equal to operator L square by 2i, where I is the moment of inertia given by mu a square. Rigid rotator. In order to study the rigid rotator, let us once again look at the expression or the relation for the kinetic energy. The kinetic energy operator, operator T, turns out to be equal to operator L square by twice mu times a square, and this then turns out to be equal to operator L square upon 2i, where I is the moment of inertia, mu is the mass of the particle, and a is the radius of the sphere. Now, having understood that I is the moment of inertia of the particle about the origin, let us also see the potential energy, and we will realize that the potential energy is also time independent. So, the Hamiltonian of the particle is then given by Hamiltonian operator H is equal to operator L square by 2i plus operator V as a function of theta pi, where operator V as a function of theta pi is the potential energy operator. Then The time-independent Schrodinger equation is written as bracket open operator L square by 2I plus operator V as a function of theta pi bracket close psi as a function of theta phi is equal to E times psi as a function of theta pi phi. Turning over to the situation of a rigid rotator in which the particle is free except for being constrained to move on the sphere so that the potential V is equal to 0, we are then dealing with the rigid rotator. The Hamiltonian is then simplified to eigenvalues of rigid rotator. Now, after having simplifying the Hamiltonian of the rigid rotator, we see that the final simplified version of the Hamiltonian comes out to be equal to the Hamiltonian operator is equal to operator L square by twice I, where I is the moment of inertia of the rigid rotator, and the corresponding Schrodinger equation can be given as operator L square by 2I times psi theta phi is equal to E times psi theta phi, where operator L square by 2I is the operator, psi theta phi are the corresponding eigenfunctions, and E are the corresponding eigenvalues, energy eigenvalues of the eigenfunction psi theta phi corresponding to the operator L square by 2I. Here the operator L square are spherical harmonics y Lm theta phi, and the eigenvalues are given as L into L plus 1 h cross square, with L taking values from 0, 1, 2 and so on. Using this, we can find the eigenfunctions of a rigid rotator, and we see that these also turn out to be spherical harmonics, that is, they also turn out to be y Lm theta phi, and the corresponding energy eigenvalues are then given by El is equal to h cross square by 2I times L into L plus 1, where L takes the values 0, 1, 2 and so on. Note that the energy eigenvalues are independent of quantum number m, that is the magnetic quantum number m, which in other words also means that the energy eigenvalues or the energy levels is 2L plus 1 fold degenerate. So what we mean over here is that since the energy eigenvalues do not depend upon m, for each value of L, that is the orbital angular momentum quantum number, the magnetic quantum number m can take 2L plus 1 values. Therefore, each energy eigenvalue will have 2L plus 1 fold degeneracy. That means there can be 2L plus 1 different m values for each value of the energy eigenvalue, or for each of the L values. And this is because the Hamiltonian of the rigid rotator commutes with the operator L, that is, it commutes with the orbital angular momentum operator, and thus one can see that there is rotational symmetry and all the directions are equivalent. So students, let us now summarize what we have learned in this module. So we started this module by understanding how the parity operations work on spherical harmonics. After having understood what parity operations are and how they operate on the spherical harmonics, then we went on to understand the explicit representations of spherical harmonics for a few lowest values of the orbital angular momentum number L, and then we drew the polar plots of the probability density distribution. Having done that, then we learnt about the vector model for the angular momentum vector L, and we also learnt what is the significance of the vector model and how this vector model comes about as a consequence of the quantization. Then we learned the wave function of a particle on a sphere. That is, how we can represent the wave function of a particle on a sphere where the particle is constrained to move on the surface of the sphere. And in order to understand this and to imply or to implement this in a real situation, we studied the example of a rigid rotator. Thank you.